In 2008, a survey known as the American Climate Value Survey was conducted by EcoAmerica and SRI-CBI. A key finding was that only 18% of Americans strongly believe that global warming is real, caused by humans, and is harmful. There is also a strong correlation between these beliefs and a person's political affiliation. The science of climate change has nothing to do with politics. The next couple of minutes will demonstrate how the Earth's atmosphere maintains its temperature due to a balance of absorption, reflection, and re-radiation, enabled by greenhouse gases. Increasing these levels of these gases increases the global atmospheric temperatures.
Do you believe in the effects of human-caused climate change?
No.
Do you believe in the effects of human-caused climate change?
I don't believe that humans have that much of an impact.
Do you believe in the effects of human-caused climate change?
Yes, I do.
Do you believe in the effects of human-caused climate change?
Absolutely.
Climate is the temperature, humidity, precipitation, winds, radiation, and other meteorological conditions characteristic of a locality or a region over an extended period of time. Climate change is any long-term significant change in the average weather that a given region experiences. Average weather may include average temperature, precipitation, and wind patterns. The term global warming refers to the observation that the atmosphere near the Earth's surface is warming. This warming is one of many kinds of climate changes that the Earth has gone through in the past and will continue to go through in the future. It is reasonable to expect that the Earth should warm as the amount of greenhouse gases in the atmosphere increase. It is known for certain that the atmospheric concentrations of greenhouse gases are rising dramatically due to human activity. It is less well known exactly how this increase in these greenhouse gases factor in the observed changes in the Earth's climate and global temperatures. The major greenhouse gases are water vapor, carbon dioxide, and methane. Other minor greenhouse gases in terms of concentration include ozone, nitrous oxide, sulfur hexafluoride, hydrofluorocarbons, perfluorocarbons, and chlorofluorocarbons. There are three fundamental ways to change the radiation balance of the Earth. First, by changing the incoming solar radiation, for example by changes in Earth's orbit or in the Sun itself. Obviously, this is not under human beings' control and not happening so far. Second, by altering the long-wave radiation from Earth back towards space. For example, by changing greenhouse gas concentrations, which is what we've been doing intensively in the past, especially during the industrial era. And finally, by changing the fraction of solar radiation that is reflected, called the albedo. For example, by changes in cloud cover, atmospheric particles, and vegetation. This is also a natural climate factor and is not easily controlled. The amount of energy reaching the top of Earth's atmosphere each second on a surface area of 1 square meter facing the sun during daytime is about 1,370 watts. And the amount of energy per square meter per second average over the entire planet is 1/4 of this. That is about 342 watts per square meter. Remember, the average includes day and night from the equator to the poles. Most solar energy has a short wavelength, close to about 0.5 microns, which is in the range of visible light. The Earth's surface reflects part of the solar energy. A significant part of this Earth's reflectivity can be attributed to clouds. In climate text, the reflectivity of a planet is referred to as the albedo, which is equal to reflectivity and is expressed as a fraction. The albedo of Earth depends on the geographical location, surface properties, and the weather. On the average, however, the Earth's albedo is about 0.3, meaning that about 30% of sunlight that reaches the top of the atmosphere is reflected back to space. Roughly 2/3 of this reflectivity is due to clouds and small particles in the atmosphere known as aerosols. Light-colored areas of Earth's surface, which are mainly snow, ice, and deserts, reflect the remaining 1/3 of sunlight. The remaining 70% of the sunlight, which is the energy that is not reflected back to space, is absorbed by the Earth's surface and atmosphere. This amount is approximately 240 watts per square meter. 59% of this incoming sunlight goes straight through the atmosphere and it is absorbed by the Earth's surface, mostly in the tropical ocean. The remaining 20% is absorbed in the atmosphere. Sunlight that is absorbed by the Earth's surface and atmosphere warms the surface and the atmosphere. To balance this incoming energy, the Earth itself must cool itself, or in other words, give back the same energy it receives. The surface cools primarily in two ways. First, by evaporating oceans into space. Earth loses some latent heat. On average, 2 meters of water is evaporated from the tropical ocean each year. In addition, small amounts of water evaporate from land and plants on land. On average, 78 watts per meter squared is lost by evaporation. All latent heat is released in the atmosphere when the evaporated water condenses as water in clouds and rain, which warms the atmosphere. Some small portions of energy is lost at the surface by thermal radiation and some convection, which is about 24 watts per meter squared on average. Second, by emitting outgoing long-wave radiation back to space, Earth rejects the rest of the energy it receives. By absorbing the incoming solar radiation, the Earth warms up like a black body and the temperature rises. A black body is an idealized physical body that absorbs all incident electromagnetic radiation. Since there is no ideal black body, all heated objects must emit electromagnetic radiation, particularly so if they are surrounded by empty space. All Earth's surfaces radiate heat, mostly at wavelengths close to 10 microns, which is longer than what radiates to Earth from Sun, and placed in the range of infrared radiation. On average, they radiate 390 watts per meter squared. This is more than the incoming solar heat, and Earth would rapidly cool if there were no greenhouse gases. 10% of the infrared energy emitted by the surface goes directly to space, mostly in polar regions. The remaining 90% is absorbed by greenhouse gases in the atmosphere. As a warm black body with a certain average temperature, atmosphere also radiates 45% of the heat that warms it to space. The remaining 55% will be radiated back to the Earth. Thus, greenhouse gases absorb radiant energy from Earth's surface and radiate most of it back to the surface, keeping the surface warm. If there were no greenhouse gases, the surface would rapidly radiate heat away to space. So the reason for the Earth's surface being this warm is the presence of greenhouse gases, which act as a partial blanket for the long-wave radiation coming from the surface. This blanketing is known as the natural greenhouse effect. The most important greenhouse gases are water vapor and carbon dioxide. The two most abundant constituents of the atmosphere, nitrogen and oxygen, have no such effect. Clouds, on the other hand, do exert a blanketing effect similar to that of the greenhouse gases. However, this effect is offset by their reflectivity, such that on average, clouds tend to have a cooling effect on climate. Human activities intensify the blanketing effect through the release of greenhouse gases. For instance, the amount of carbon dioxide in the atmosphere has increased by about 35% in the industrial era, and this increase is known to be due to human activities, primarily the combustion of fossil fuels and removal of forests. Humankind has dramatically altered the chemical composition of the global atmosphere, with substantial implications for climate.